Okay, recording's going. Do you want to start? Is it Alif?
Yeah. My name is Alif. So I'm currently working in Women in Digital as a junior project manager. And I've completed my bachelor's majoring in computer science and engineering. So I do have a decent amount of knowledge in programming and coding in general. But this concept of blockchain, I did go through it in the past, not too much, but I am somewhat familiar with blockchain, cryptocurrency, stuffs and concepts related to these. So yeah, I'm really looking forward to this course actually. I'm gonna get to learn a lot.
Awesome. Mumita, sorry if I'm pronouncing names wrong.
My name is Momita Marcus. I am in Women in Digital for 2 years now. I am an Android developer. I basically work with Java and I do programming in Java.
Yeah.
Blockchain is new for me. I never heard it before, but recently I do some research on blockchain. It seems quite interesting to me. I'm looking forward to it.
Cool. Nice to meet you. And as I don't know if he's connected.
Yeah.
Maybe not. Okay, well, I'll go on with firstly just a really quick overview of what we're going to be covering, and then we'll start straight into it. So the first kind of 5 weeks will be focused on, broadly, what is a blockchain? How is it used? What are the major kind of blockchains and technologies out there? Different cryptocurrencies and smart contracts and things like that. So the first 2 weeks will kind of be covering that on a general level. And then we'll really get into specifically the Ethereum blockchain, because it's the most widely used by a number of users. And it's also the most widely used blockchain for smart contract development and for building applications using the blockchain. So that's what I use at my company and what I've used in the past. So I think it's a great place to start learning how to develop with blockchains. And as part of doing that, we'll also look at the smart contract language called Solidity, which is probably the main language used for smart contracts. Then in the second half of the course, so weeks 6 to 12, we'll focus on a few projects, both that we'll kind of do together during the call, and also kind of take home stuff to work on if you're interested. So first focusing on building out just smart contracts. So building out smart contracts that we deploy onto Ethereum, both a type of token called an NFT, which I'll talk about, and also a kind of way to issue digital certificates that say that something is correct. So you might be registering that your car has a valid license plate, for example. So we can build a sort of registry like that that's in a smart contract and that's tied back to our digital identity. Then the final project is building out a kind of simple but full decentralized app. So this is not just building the smart contract, but also building the user interface that people can use to interact with the smart contract, seeing how to connect it to our wallets, and seeing how to kind of use it with multiple people. And the application that we'll be building is something called a decentralized autonomous organization, which is a bit of a mouthful, will probably make more sense later, but it's essentially a democratic organization that's on the blockchain. So people can participate around the world, vote on decisions, send money, perform actions, and so on, all without putting trust in anyone. So it's a really cool use case of blockchain, and it's a cool app to build. Maybe throughout, I probably will talk quite fast. It's a bad habit, but if you've got any questions, either just straight up interrupt me or type in the chat and I'll get to it as soon as possible. Cool. So this week, it's answering the simple question, what is a blockchain? So if you've looked it up online, you might see some really kind of wordy definitions like this one. So they all kind of assume that there's a lot of knowledge already. You already know a lot of things about cryptography, about databases, about peer-to-peer networking and things like that. What I wanted to do instead was start from kind of the most basic functionality and then build up a blockchain and build up the definition of a blockchain along the way throughout this call. And to do that, we'll be looking specifically at Bitcoin. So you've probably all heard of Bitcoin. It's pretty crazy right now. It's a cryptocurrency. So it's a digital cash equivalent. You can send money to people. You can have a wallet and store your money, and you can use decentralized applications all using this digital currency. But you don't need any banks or you don't need any governments kind of verifying that that money is real. So it's kind of the first digital currency, or the first widely used digital currency. And because it's quite simple, it's a good place to start with our definition of blockchain. So simplifying that definition, we can really summarize blockchain as this, again, with a lot of words. Just admit someone to the waiting room. A lot of words that probably don't make much sense right now. So it's a blockchain, or any blockchain, is a space-efficient, distributed, tamper-resistant ledger. It was first kind of proposed in 1982. So there was some initial work done by a man named David Chaum. He kind of came up with the idea in theory, but the first time that it came onto the stage in terms of implementation and software that was widely used by people was in 2008. And this paper called, I think someone else has just joined. Hello.
Our another student.
Hello, welcome. I'll just carry on. If you've got any questions, put it in the chat as well. So this paper was released online that was called Bitcoin, a peer-to-peer electronic cash system. So one of the cool things about this is that the author, Satoshi Nakamoto, doesn't really exist. It's a pseudonym and no one knows who is behind this name and who published this original paper. So nobody really knows who invented Bitcoin. But essentially, Bitcoin was in 2008 the first true blockchain that was widely used. It's definitely not the only blockchain now, and it's not the only use case of blockchain. So being a cryptocurrency, it's kind of one use of blockchain, but it is the most widely used and the most popular use case of cryptocurrency. So you've probably all seen the Bitcoin price at the moment. In 2021, the total kind of value of cryptocurrencies, so purely digital cash that runs on a blockchain, has now reached $1 trillion US. So this is enormous. And it all started just in 2008 when Bitcoin was worth, say, 0.0001 cents. So let's go back to that definition. And we'll start with just a ledger. So we'll ignore everything else here. We don't care about these properties. We're just going to look at a ledger. And you might be familiar with what a ledger is. It is essentially a database of sorts, right? So we store data, we can retrieve it and read it, and then it is it. But the way a ledger works is that instead of having our database, which we're constantly changing, we're instead adding things to our database. So if we think of the example of a cryptocurrency, we might traditionally, if we're using like an SQL database or we're using app storage on Android, we might have, say, 3 users in our system, which we'll call, let's go Kagel, Mila, Alif. And if we're representing a cryptocurrency, we might have a balance for each of them. So say I start with 10,000 and the others start with 0. And this is our money. So if I was to then transfer $100 to Mila, we would, in a kind of database transaction, change these values so that it looked like this. Right? That's all pretty straightforward. And over time, we would keep updating our database, changing the balances. People could log in and view their balances. And this is pretty much how a bank works. Your money is just in a database like this. But where this becomes tricky is then when you want to go back and see what happened in the past. If I just look at these 3 numbers, I really don't know if Neela started with 10 billion or if she started with 0. So if we instead consider this as a ledger, we can record the changes that have occurred to the database rather than only the current database state. So it might look like instead Cadle transfers to Neela $100. Then Neela transfers to Alif $50, like this. And so over time, we're never removing information or editing information, we're only adding it. And this gives us kind of that full history of what's happened with the cryptocurrency. Then if you want to check the balance, what we have to do is kind of combine all of these updates one after the other, and we end up reconstructing the final balances like this. So we'd first apply this transfer from me to Neela, then from Neela to Alif, and we end up with our final balances. This is obviously in currency quite useful because you want to see the history. It's also useful for many other applications. Say you've got a truck going through Bangladesh and you want to see all the places it stopped at and make sure that the temperature of the truck was never over a certain limit, because that would void the warranty of the food that it was carrying. You want to be able to go back through all those stops and see the full history. Now, of course, you could do this with a normal database, and plenty of people do. But as we'll see, blockchain has a number of properties that make it really great for that. Are there any questions so far? This is pretty straightforward so far, I think. Cool. So in Bitcoin and in a lot of cryptocurrencies, we take this ledger and then we split it into blocks. And a block might occur every 2 seconds, or it might occur every 1 minute or 1 day. And a block is really just a group of these items. So we might have block 1 being these transactions or these transfers, block 2 then being another set of transfers, and then they're parceled into these specific blocks. Now, when we start with our initial database, which might say that everybody has 10,000. We call this kind of initial first block, or like block 0, the genesis block. And the idea is that if we have the genesis block and then we have each block after it, we can end up with our final bank balances. So we can reconstruct that whole database. To do that, what we use is something called a state transition function, which is just a fancy term for a function that takes in the database, adds a block to it, and then results in a new database. And we can see that in this diagram here. So we start with the current database state, which right at the start is this. And then when each new block appears, so first block 1, then block 2, we run that state transition function and we end up with a new database state, or a new state of data, which in our case is bank balances. Now, what makes a lot of blockchains unique and different to each other is that this state transition function can really be anything. So in our use case, what we've got is a function which transfers money between people. And that's what Bitcoin does. It transfers the cryptocurrency between accounts. But if we look at a blockchain like Ethereum, it can use its state transition function to run a whole virtual computer, where instead of it being transactions between people in these blocks, we have computer instructions written in a programming language, and so on and so on. So there's a bunch of state transition functions. For now, we'll just focus on cryptocurrency because it's quite simple to understand. But that's the general principle.
I had a question, Cadle, if you don't mind me asking.
Yeah, go for it.
Regarding the state transition function, does it stay fixed after every transaction, or does it change?
That's a great question. So the rules of the blockchain are set by the people who control it. So we'll get to that kind of decentralized aspect later.
Okay.
But if everybody agrees that the state transition function should change, then it can. But if people are kind of undecided and you don't have a majority who wants to change it, it will stay like that forever.
So basically it depends on the consensus of the entire
Yeah,
network.
exactly. Yep. Yep.
Okay.
So you would need 51% consensus, so more than half of people voting to change that function.
Right. Got it. Thank you.
So what I would recommend too is grab this Bitcoin paper, the paper that released Bitcoin, It's literally 9 pages long, and it's actually really easy to read, even for, computer science papers tend to be quite complicated. But if we scroll down to chapter 3, we can see a description of what I've just described, right? We've got blocks containing items, and that's where I got that diagram from. And it will build it up as we have. Okay, so we've got our database here, but there is already a problem, and that is it's not tamper resistant in any way. So if someone else came into this system, say Alif, and he wanted to suddenly become a lot richer, he could go back to block 1 and he could say, change the value that I transferred to him to be 10,000, right? And essentially rob me of my money. And this is the problem with databases, right? They have to be secured. You have to have access control. You have to have a kind of rigid procedure for making changes and so on, because without that, people can just come in and steal money, right? And that's what happens when a bank gets hacked or when your application gets hacked. People just change the database state and then you're stuffed, basically. So what would be really great is if we could have this ledger be tamper-proof, so that once we've got a block, we can't go back and change it. So this is that second part of the definition. We're going to extend our definition of a ledger to also include tamper resistance. And the property that we want to hold is that after we've added a new block, by having, say, block 2, and everybody knows what block 2 is, previous blocks cannot be edited without us knowing. That's the property we're looking for. Now, to do that, we're going to have to take a quick diversion into cryptography. So this is a very wide and complicated field that I don't know a lot about, but generally cryptography is any method of storing or transmitting data in a form that only allows people who have permission or who are intended to read it to be able to read it. For everyone else, it's nonsense. Blockchain in general uses cryptography everywhere. So you'll see it in addresses and wallets and transactions between people, and the peer-to-peer network is everywhere. But what I particularly want to focus on today is kind of 3 devices or techniques in cryptography. The first being hash functions, then asymmetric keys, and finally Merkle trees. And we'll get to each of these. But firstly, what I wanted to do was start off with hash functions. And you might already have encountered these, I'm not sure. But what a hash function is it's essentially a function that takes an input and gives us an output. So we can see here, Fox becomes this. The output is often called a digest. Not sure why, but it just is. But the kind of unique property of this cryptographic hash function is that if we have the digest, we can't get back to Fox. It's a one-way function. So Fox will always, when put into this function, result in this digest. But without knowing the original input, we can never go the other way. And you can just go on a website like this. It's SHA-256 online. And this is a particular hash function called SHA-256. And you can test this out. So we can see if I type in A here, and then it becomes hashed, we get this long string, right? And if I type in AB, that changes, ABC, and so on. And every change we make to it changes that hash. But if I just had this FDB hash, I would never be able to get back ABC, DASD. So it's really cool that it works one way. Then the second kind of property that makes this so interesting is that with a few exceptions, any input will result in a different output hash. So even like changing one letter will give me a wildly different hash. Theoretically, it is possible that 2 inputs would result in the same output hash. However, nobody has ever found one for SHA-256 and for most other hash functions. And if you were to find one, which is called a collision, say if A and AB both result in the same hash, that's a collision. If you were to find one, you would probably be pretty famous because you'd break the entire internet's encryption. So far we're reliant on there not being any collisions in these schemes, and it's working out. So how can we use these hashes then to give us that tamper resistant property that we're looking for? Well, one way, and the way that Bitcoin kind of does it, is that after it generates each block, it takes the contents of that block and it hashes it like this. So we now know that block 1 has that hash. If then I were to receive block 1 from another person, and I knew that the hash of block 1 was that, then I could just verify it by rehashing block 1 and checking if it's the same hash, right? So going back and looking at the block, I can say that the contents haven't changed from what I think they should be. But if I didn't have this hash in the first place, there's no way for me to tell kind of what it is without trusting the person who's given it to me. The way we get around that is by having each block contain the hash of the previous block. So block 2, instead of just having these new transactions, also contains the hash of block 1. Then we take the whole block 2 and we hash it. And then if we have a new block 3, it starts with the hash of block 2 and so on. So we kind of get these links here. And then if I've got block 3 and I look at the rest of my database, I can check the hashes of each of the previous blocks to make sure they haven't changed because I've got that link. And what that ends up looking like is a bit bigger. So you can see here how each block has the hash of the previous block, and that provides the links. Then if someone were to go to say block 64, change one of these transactions, the hash of this block no longer matches the hash in the next blocks. So once you've got a later block, you can verify that the entire previous chain, so the block chain, which is where it gets the name, is valid and hasn't been tampered with.
Sort of looks like a linked list.
Yeah, exactly. It is exactly like a linked list.
Linked list. Okay.
So these hashes are kind of the pointers to the previous block.
Right.
Yeah. So that's awesome. We've got our we've now got our tamper resistant ledger, but it's really no use just being on one computer because then I'm the only person who can access the cryptocurrency. I can't trade with other people, and it's still in kind of a single point of failure, which is me. What we're going to do next is we're going to add another property of our blockchain, and that is that it's distributed. So to kind of work out what distributed means, we have to introduce some more terminology. We have to think about networks, and networks are either people, for example, right? I know certain people, I know everyone on this call, I know my family, then my family knows other people and so on. And so by connecting the links of all these people, we get a network. And this is the computer network that you're all familiar with, the internet, all of these things are networks. Here, the network that we're all pretty used to in computer science is a centralized network. So we can see that all of these users, the blue dots, are connecting into a single server, right? So if you think about your bank, everybody who opens their bank app is connecting into that bank server. And then the bank can, provide information, you can add information to the app and so on, which is great, but it has a bunch of disadvantages. So some of the problems with centralized networks like this are you have to trust the bank. So it's not trustless. You're relying on one person or one group of people to always do the right thing. And as we've learned in the past, that doesn't always happen. Even governments, big corporations, non-profit organizations, all of these people in the past have committed fraud or broken the rules and so on. And in a centralized system, there's nothing you can do about it. And there's also usually no way for you to tell. The bank controls access to the data. If they want to change it, then you don't really know. Some other disadvantages, it's a single point of failure. So if the bank has a bug in their software or their server goes down, nobody can access their banking app. Imagine if this is a hospital system that contains patient data, right? And in the middle of a particularly busy night at the hospital, the system goes down. It can lead to actual patient deaths, right? Yeah. So having a single point of failure is really quite an issue and damaging in a lot of industries. It also, by having everything in a single location, it makes it really vulnerable to hacking and cyber attacks. It's a single kind of big score to get that. If you take control of this one server, you get everyone's data. It also means that whoever controls this centralized server can control access to it through things like the price. They can keep raising the price and there's nothing that any of these people can do about it. They can do anti-competitive things like preventing a user from exporting their data. Right, so say right now we want to move from one bank to another. We can't export the whole history of one bank and then move it into another bank. Right? The banks don't want that because they want you to stay within their app. Right? Same as say you've got an Android phone and you're moving to an iOS phone. You can't move a lot of the data. You can move some of it, but not all of it. Right? So we end up building what's called a walled garden. So you've got this nice, beautiful garden that works well, but there's a wall around it. And the only people allowed in the garden are the people who control that centralized point. I'm trying to think if there's any other disadvantages. You're also kind of reliant, I know we were talking before about the state transition function. You're reliant on one person to change that. If there's a bug or if everyone wants to change the rules, one person makes that decision and one person only. If half the bank's customers decide that the bank is taking too much interest, for example, they can't vote to change that interest. It's up to the bank and they have no choice but to accept it or to leave and lose all their data. So that's another disadvantage. So on the other end, on one end, we've got centralized, and then the complete opposite is what's called distributed. And here we can see it's pretty self-explanatory. Instead of having that single point where all users interact, we have users interacting with each other. And this is just like a network of people, or friendships, or if you've used BitTorrent to download files, it looks like this. Every computer or every person is connected to multiple other people, and you kind of build up this mesh. What that means is that, say, this pink dot here goes offline, well, everybody else can still talk by jumping through the other nodes. It's kind of healing and it's resistant to attacks. You lose two nodes or two computers on that network, the others can still communicate fine. It also means that we can make decisions together as a unit. It's resistant to censorship. So you'd have to censor all of the nodes to stop information passing through. We don't lose data. If a couple of our network nodes lose their data, everyone else has it so they can get another copy and so on. So it's really quite useful. In this diagram, we've got kind of two types of distributed ledger. In the pink one, each of these users are anonymous. So anyone can join this network. And this is, say, the internet, right? Anyone can join the internet. You're anonymous unless you put your name on it. It's kind of free and open to all. And this is what we'd call a public ledger or a public blockchain. On the other hand, we might have this blue network where each of the users is known and you must get permission to join the network. So this could be like the employees at a company, right? You all know each other. So it's a distributed network, but you have to be hired to be allowed into it and your identity is known. Otherwise, you wouldn't be able to validate whether someone should join the network. So these two types are both distributed, but they kind of come with disadvantages and advantages, which we can talk about a bit later as well. Okay, so then since we've got kind of now an axis between centralized and distributed, we've got the two polar opposites from each other. There's also a middle ground, which is known as decentralized networks. And here you can see we've got this almost hub and spoke pattern. So we've got a bunch of little distributed networks that are connected together. So we have groups of users who connect to a shared system that then talk to other systems. And this is kind of how email works. So each user connects to their email server, whether that's Gmail or Yahoo. Then the email servers talk to each other to pass the messages. And this can be a really good kind of middle ground between the two types of network. You've got you now have multiple points of failure, right? So if Gmail goes down, it doesn't stop everyone else's emails passing between. But users can then have a choice of which provider they go with. Like I might prefer the Gmail interface, someone else might prefer Yahoo. And it's usually pretty easy to move between these systems as well. I can export my emails and load them into a new service. So it's a nice middle ground. but it's not kind of as pure and distributed as these ones, right? These users are still relying on a single point of access, which can go down and lock them out. Okay, now hopefully that makes sense. So when we're thinking about blockchains, we're talking specifically about distributed networks. So when we have our cryptocurrency, we don't want a single bank or a single government controlling our money, or in kind of Bitcoin's case. What we want to do is be able to send money to anyone we want. And we don't want a single point of failure that controls who we spend money to. We want to be able to just kind of do it peer-to-peer, so connected to everyone in a distributed way. So to do that, we have to take our ledger, which we've got just on our own computer, and we have to share that across the world. So everybody should have a copy of the same ledger that contains these balances. And then if I wanted to transfer $50 to a leaf, I would just add it to the ledger and share it with everyone else. And that all kind of works in theory, but the difficult problem that blockchain solves is trust. There are a couple of kind of problems with just this naive sharing of the ledger. So if I transfer my money to a leaf and I send that to everyone and say, add it to your ledger, that's all well and good. But I can start to do bad things. The first kind of problem that we have is called double spending. And in this diagram, you can see we've got a single Bitcoin. And if I'm just saying, oh, my transactions are valid, I'm going to send it to everyone, include it in your database, then what I could do is spend the same money twice. So we go like Cadle to a leaf, $10,000, Cadle to Nigla, $10,000. Now I've spent my $10,000 twice, which is illegal in the rules of the cryptocurrency we've set up. But without a way to validate that and agree on what's right and what's wrong, then I can do this. There's no way to stop me doing this. And that's the double spending problem. Does that make sense, the double spending?
Yeah, it makes sense.
Cool. Okay. So then the more general, I guess, problem with the distributed network is what's called in computer science the Byzantine generals problem. And this scenario is kind of a little thought experiment. So say we are a bunch of generals, we've all got our own little armies, and we want to attack this big castle. It's only going to work if we all attack at once. So if we all attack at once, our combined armies have enough power to overrun this castle and get all the gold within it. If we all retreat, then that's fine. We just don't attack the castle at all. So in this case, coordination, whether we choose to all attack or whether we choose to all retreat, leads to a good outcome, right? We either win or there's no losses. The problem comes when some of our generals are traders. And in the money case, I'm the trader here. I'm trying to spend my money twice. If some of the armies attack and some of the armies don't, they're traders and they retreat, then all of these armies are wiped out. And the whole, the generals in kind of common are defeated. And it might seem like kind of a silly analogy, but if you think about that in terms of blockchain, maybe we have all of these generals who are attacking have agreed that I can only spend $10,000. They've said that this is an invalid transaction. Like I've double spent my money, that's not on. But then all of these traders who I'm friends with say, actually, we're going to allow that. You end up with half the network saying this is allowed and half of the network saying it's not allowed. And the blockchain kind of collapses. No one can decide on what's true. You might end up with multiple database states. So some people will have a different balance in a certain node. Some will have a different balance in another node and so on. And you end up with the defeat of the whole network. And this is kind of the main problem to solve when we want to take our ledger and decentralize it amongst the whole world or the whole network. So the way we solve this is with what's called a consensus algorithm. And consensus really just means the whole network agreeing on what is true. That's all that it means. But you have to do it in a way that is secure. And that means that the whole network, that some parts of the network can't break the rules and other parts can't. Everyone has to agree on what's true. or else you get people double spending money, you get people taking money that isn't theirs. In the case of Ethereum, you might get someone running a program incorrectly to deliberately give themselves tokens or something like that. So the consensus algorithm is kind of the key innovation of a blockchain that allows this database, this tamper-resistant ledger, to then be distributed amongst the network. Now, what I'm going to talk about in most detail is a consensus algorithm called proof of work. The reason that we'll focus mostly on this is because most of the large blockchains in operation, so Bitcoin, Ethereum, Zcash, Monero, all of those cryptocurrencies and blockchains all use proof of work. So let's make up a scenario. So we've got, say, 3 computers, and we'll call them A, B, and C. Now, each of us has transactions or has, money that we want to send. And so we're each going to create a block. So if we all send maybe I'll just label these differently to say that they're all block 0 in our minds, but they contain different things. So the computer A has a block with certain money transfers. Computer B has a block with different money transfers. Now we've all got our new blocks, and then we want to start sending that to each other. If we will all end up receiving 3 copies of one block 0, but they're not interchangeable in any way. So we can see that in this scenario where everyone's just creating blocks whenever they want, the system kind of doesn't work. There's no way for us to decide which block we should include in our ledger and which block we should reject. We kind of need to all agree on one block 0 and include that in our ledger. So the way proof of work operates is it allows us to slow down this creation of blocks and make it so people have to work really hard to be able to create a new block, and make it really easy to validate a block. And it might make more sense when we come up with an example, but essentially it's a way of using computing power to secure the network. So the way proof of work operates is that if I take, say, our example block here, block 1, I'm going to add to it one more item. So we've got currently all our transactions. We've got the hash of the block. I'm going to add one more item, which is called a nonce. And the nonce will start at 0. And the idea is each node in the world, so A, B, and C, will have received a bunch of transactions. So they'll have certain spending, and they want to include it in a new block. So to do that, they first have to find a valid block using proof of work. The way that works is that we have a difficulty, and the difficulty can change over time, but you can think about it as the number of zeros that have to be at the start of the hash. So if I have a difficulty of 1 for simplification, then my block is only valid if I have 1 or more zeros at the start of the hash. And when I get these new transactions and I start creating block 1, I start just bumping up this nonce one by one. So I go 1, 2, oh, that was easy. So a nonce of 2 we found gives a hash here that has a 0 at the start that's over the difficulty. So this block is valid with a nonce of 2. Now, in reality, it's a lot harder than that because it might be 16 zeros at the start. And even though computers can do this extremely fast, if there's 16 zeros at the start, it takes a long time and it takes a lot of computational power. So if we look at, say, this graph here, we can see that just us as, just me typing in numbers, I can do maybe 4 calculations per second if I'm really fast by adding this number. But the total Bitcoin network as of now does about, let's say, nearly 200,000 petahashes per second. So that's I don't know, some 1,000 billion or something like that. That's how much power is needed to secure the Bitcoin network. And that's because you might require a hash with like 18 zeros at the start, for example. Okay, so that's the kind of nonce. And so to make a valid block, you have to find a nonce that gives you the hash with a certain number of zeros. Now, the reason that then this works is because we use this consensus mechanism, which roughly works like this. So let's step through each of the steps one by one. This is from the Bitcoin white paper. And again, we'll start with our 3 nodes, A, B, and C. In step 1, we get new transactions to all nodes. So say we've got a transaction TX1, which might be, Cadle to a leaf. And we've got TX2. Maybe B receives TX1, C receives TX1 to 3. Right, so that each have got these transactions. Now they want to put them into a block. So they'll do that as before. They've each got a block that contains the transactions they've received. Now, to determine who wins, we need to race to find a nonce, or the number that we're incrementing, that gives a hash that matches the difficulty level. So that's step 3 here. We start incrementing the nonce. So A starts generating 1 million hashes per second until we get 18 zeros at the start. B does the same thing, and so on. Then let's say B wins. So B is first to find that. It works out that the nonce is 1001 or 10,001. So because it's 1, it knows it has a valid block, and it's going to send its block 0 to A and C. So then everybody has this block 0. A and C haven't finished. They haven't found a valid block. So they accept B's instead. And then everybody agrees on the same value of block 0. So nodes accept the block only if all the transactions in it are valid, and if it's a valid proof of work validated block. Then everybody starts again, but this time they're trying to build block 1. And so in that way, we've kind of built up that decentralized ledger. Now, you probably have noticed this, but there's still kind of an issue here. And that is that, say, A and B both find the nonce at pretty much the same time. So A also works out a nonce for their block, which is that. And A starts sending out its block as well, because it's got a valid block. B sent out its valid block, even though they're different. And about half the network has worked out A, half of the network has received B, and we end up splitting the blockchain here. So in this case, we have block 100. We then have 2 block 101s, one which has been received by some of the network and the other which has been received by the other part of the network. And then these parts of the network independently start generating more blocks using that consensus mechanism. And we end up with what's called a chain fork. So you can see that we've got 2 independent blockchains that have split off from this single block. Now, the idea of kind of the proof of work consensus mechanism is to make it really hard for 2 blocks to be created at the same time, so that we don't have as many of these forks, so that everybody will start agreeing that this is the actual blockchain. We'll get rid of this chain fork. So we mark it as an orphan. We say these blocks are stale, and these blocks essentially get deleted from the network, and everybody switches over to this chain. The way that's implemented, it's usually whichever's the biggest chain wins. And so we continuously get tiny little chain forks when people find a block at the same time that then get collapsed back into one by deleting the smaller chain. Then we have the concept of a confirmation. So if we think about this block 101 containing transaction B, whereas this other block 101 contains transaction A. If we've had 3 blocks after transaction B, we can say that transaction B has been confirmed 3 times. There's been 3 blocks after transaction B to confirm that it's really in the main ledger, whereas transaction A has only had 2 confirmations. If then this chain wins, so this chain of the fork wins, and we delete this whole chain, transaction A is lost. It's like it's rolled back. That money was never transferred. So we can say that the more times our transaction is confirmed, the more sure we are that our money has been spent in the global network. So a single confirmation or two confirmations might not actually be enough to know that you've paid someone successfully or that you've received money successfully so you can send the goods and so on. So in Bitcoin, usually the recommendation is to wait for 6 confirmations. So you generally want to make sure that one chain is 6 blocks ahead of your transaction before you either you send your goods that you've just been paid for. Otherwise you have the risk of the money being rolled back. Okay, so let's look at just going to try and find just to kind of illustrate this. If we think about proof of work being really difficult, we want to restrict the length of time it takes to create a block so that we're not getting all these chain forks, so that blocks are produced at kind of a steady rate, but not too closely together. And we can see this in a block time chart. That as of kind of now, each block is created in about 12 minutes. Right, so that's what the Bitcoin kind of difficulty has set it on. And that means that if you want to wait for 6 confirmations, you might have to wait for 6 times 12 minutes, so over an hour, right, to be sure that your money has been spent, which obviously isn't that practical for a currency. You go to buy a juice at the shop and you have to wait an hour for them to make sure they've been paid. So that's kind of one of the problems with Bitcoin. In order to keep this block time relatively constant, the network can change the difficulty automatically. So if you imagine you have a bunch of people continuously coming onto Bitcoin and adding more power to the network, you would kind of assume that this block time would go down because the more computing power available, the quicker to find a block using proof of work. And we can indeed see, if I go to the network graphs again, that the total kind of speed of the network, the total computation power available, has increased massively from 2008 when it was created to now, right? So we would expect, if we didn't change the difficulty at all, for the block times to be coming down proportional to this. It's looking like kind of a downwards line. What we do though, is we can, if I find it, that's not it. We can see that we're increasing the difficulty of finding a block over time, so that that graph of the computer power and the graph of the difficulty kind of cancel each other out, and we end up with that flat 10-second-ish block time. And so by increasing the difficulty, we're essentially saying we need you to find more zeros at the start of the hash, from 0 right at the start up to like 18 now, or whatever it is. Okay, so finally, the point of proof of work, because this is all a lot of talking and not a lot of use yet. The point of proof of work and consensus mechanisms in general is, as I said, to avoid double spending and cheating and lying and so on. The kind of risk that the network is facing is something called a 51% attack. So if you control 51% of the nodes, and all of these 51% of the nodes start agreeing on transactions that are incorrect. So they start saying, yeah, it's okay for you to spend your money twice. And these bad nodes are like the traders in that Byzantine general problem. So if enough of them agree, if more than half the network agrees, then the naughty chain or the incorrect chain will eventually be selected. So you can see here, we've got more good miners than bad miners. So a miner is any node on the network that's creating blocks. We have more good miners than bad miners. So the chain where all the rules are followed is being selected. The bad miners, there's only one of them. So even though they're creating another block, no one's using it. So the money is safe in this chain here. But if instead we had more bad miners than good miners, they could switch the network over to using this bad chain and double spend money or create money out of thin air and so on. So they could essentially take over the network and start breaking the rules. By using proof of work and making it really hard to generate a new block, that means that to take over the network, you need to have 51% of the computer power of the network. So rather than just 51% of the nodes, you need 51% of the computer power. And as we saw in those charts, that level of computer power is pretty much impossible. So you would need to control, say, China's worth of computers in order to take over the network. And that's why Bitcoin is so secure, is that it's economically impossible to buy that amount of computer resources. Like I don't know if you could even do that. I don't know if there's enough computers in the world or GPUs in the world. And that's kind of what proof of work and all the other consensus algorithms really boil down to. We want to stop 51% of the network being able to create their own chain that breaks the rules. So if our consensus mechanism can fight this, then it means that the whole world can agree on what is true in the blockchain and can agree that the rules have been followed. I'll pause for questions if anyone's got them on proof of work. It's a bit complicated. Okay, cool. There's one more little thing to add.
I want to know if my network is big, like I have lots of nodes or blocks, then it take too much time for doing proof of work. Like if any transaction I creates happen, then it broadcasts to all the nodes, and then it's linked to all, and it checks all the hashes. Okay.
Yep.
So does it take too much time if network is big or so?
Yeah, great question. So I think if I'm understanding your question correctly, what you're saying is that does it take too much time to validate all the previous blocks when you're using proof of work, when you receive a new block?
Yeah.
So if we go back to this hash function, so if I want to find one that say starts with 2 zeros,
okay,
and I'm increasing the nonce and so on, it's going to take me ages, right? I'll have to type them all in and so on. I don't know if I'm going to find any. Let's say 1 0. 21, 22, 23, 24. So you can see if you need 18 zeros, this takes a very long time. Oh, we're going to get there soon. Let's go. Maybe not. All right, so this is me trying to mine a new block now, right? I'm looking for a valid block that's above the difficulty. Oh, there we go. All right, so I found it and I sent my block to everyone. But because the nonce is part of the block, to validate it, all I need to know is this nonce, the block, and I can just type that number in directly, 55, and go, yep, it's got 1 0, so it's done. So instead of having to do 10,000 hashes, I can validate a block with only one. And that means that if there's, say, 600,000 blocks, then I only have to run 600,000 hashes in total to go back through the whole network and validate all those links. So it's a lot faster than creating new blocks. But in practice, if you were to install a new operating system on your computer and try and download the whole Bitcoin blockchain, which is quite large at this point, having been run for 12 years, it would take you maybe 3 days to validate the whole network. So it's a lot faster than mining all the blocks, but it still takes a while.
Yeah. Got it.
Okay. So something to discuss generally when we're talking about blockchain is the field of crypto economics. And this is kind of an emerging field that draws on a lot of research previously in game theory and mechanism design and auctions and things like that. But essentially it's the use of incentives. An incentive being, a carrot or a stick that you use to get someone to do what you want, to make the system work. And what we need in Bitcoin to make the whole system work, because it uses this proof of work consensus mechanism, is we want people to be mining. We want people to be generating all those hashes and trying to find new blocks. So there has to be something in it for them, because it actually costs money to run your computer, use electricity, your computer wears out and so on. So they need to receive a reward of some kind. And in Bitcoin, whoever creates a block that's then accepted, so say A's block here, block 0 is valid and accepted, they get a reward of new Bitcoin. So in that way, you end up with, profitability from securing the network. Okay. Let's go on now to other consensus mechanisms. So remember, consensus in general is just about making it hard or impossible for 51% of the nodes in the network to agree to break the rules. It makes it really, really hard to take over half the network. Proof of work is the most common, but it's not the only consensus mechanism. So another one that we have, or another family of consensus algorithms, is called proof of authority. In this, instead of the network being secured by computing power, it's secured by identity. And this is usually used when you have a decentralized network where you have to permission people to join you. So when no one's anonymous and we know everyone. So say everyone on this call was in a network, proof of authority might be as simple as saying, oh, we trust Cadel, he can create all the blocks. So it's definitely not as secure as proof of work, but it still prevents that attack because we're trusting me to make the blocks correctly. Obviously, that doesn't work with an anonymous network because we don't trust everyone. We don't know who they are. They could be anyone. But say you guys trusted me, proof of authority works fine. More kind of advanced proof of authority networks that might contain, a bunch of companies. So Facebook was working on its own cryptocurrency, where the members in the blockchain were companies like Facebook, Google, Apple, Yahoo. All of these people are running their own nodes. Maybe they don't trust Facebook to run the blocks themselves, to always be acting correctly. Maybe instead, all of these nodes want to essentially vote on which block is correct. So all the companies will get together, they'll look at the new block, and then they'll submit, yes, we think that's valid, or no, we think that's invalid. And we end up kind of deciding based on a majority vote. It's like an election for the new block. And this is kind of how proof of authority mechanisms like IBFT and Raft work. So IBFT literally stands for Istanbul Byzantine fault tolerant. So that's the Byzantine generals problem. It's saying that it's tolerant to that problem. It solves it by using that kind of proof of authority election algorithm. You don't need to focus on that too much unless we're dealing with a private network, but that's kind of useful.
So the proof of trust is based on the number of votes.
Yeah, that's right. So if we look at this kind of scale here, the trade-off for all of these consensus mechanisms is between performance, so how fast the network runs, and how secure the network is. So down the bottom, in terms of the worst security but the fastest performance, is that kind of proof of authority where we're just trusting one person. So we're trusting me to create all the blocks and we're all going to agree on it. Obviously, that's fastest because there's no need to vote or anything like that. Yeah. But it's the least secure. There's a single point of trust, which is what we're trying to avoid with the blockchain in the first place. The kind of other end of that, so the most secure, but the slowest, is that proof of work that we were talking about. And then in the middle, we have the voting mechanism, IBFT or Raft, where you need, say, half of the nodes to vote that this block is correct. And then that's kind of a good middle ground. And at my company where we're using a private network, we're using this IBFT 2.0 algorithm because it's kind of a good mix of performance and security. So we've got nodes running, in the US and in Singapore, and they can agree on blocks within like a 2-second block time. So if you compare that to a 12-minute block time in Bitcoin, it's definitely a lot faster for things to get done. There is another consensus mechanism that we'll call proof of stake. And this is very new. It's kind of just hitting the hype at the moment with a network called Chia. And I don't really understand how it works yet. I haven't looked into it too much. But instead of being secured by hash or by computer power, the network is secured by how much storage space you have. So if you have 10,000 hard drives, you have a higher chance of creating a block than someone with one hard drive. It's supposed to be more sustainable than Bitcoin, but it's also, you also need 10,000 hard drives, so it's not really that sustainable at all. So as I said, proof of work is the most common consensus algorithm, but it has a pretty huge downside, and that is that it uses an enormous amount of electricity. So we can see that in this diagram, I think this is from 2018, so it's much worse now, but this is the energy that's required to generate $1. So you can see that, say, Bitcoin requires more energy to generate $1 than mining, mining copper from the ground. Right? If you took Bitcoin and took all of its electricity use from all the computers on the Bitcoin network around the world, it would be something like the 31st largest country in the world in terms of electricity usage. So it's pretty wasteful in terms of the carbon pollution it creates, the amount of electricity it uses that could be used for better purposes. And that's left a lot of people looking for a solution that's still as secure as proof of work, but has less of an environmental impact. The kind of up-and-comer consensus mechanism that Ethereum is going towards is called proof of stake, and it aims to address this problem. So instead of being secured by expensive computing power, it's secured instead by the amount of money you own. And it's a trade-off, It's not necessarily the most fair to secure it based on the amount of money you own, but it's better than proof of work in that proof of work, you already win if you have the most money, right? Because you can buy the most computers. So this is kind of cutting out the environmental impact anyway. And you end up with this other consensus mechanism that's still as secure, but does a lot less damage. And you can look at this diagram if you want a bit more detail. There's not really any large networks using proof of stake yet, but Ethereum is moving towards it and will probably by the end of this year be using proof of stake, which is great because you say it's the 4th largest producer of cryptocurrency carbon emissions in this chart. So it'll be great. Okay. So we've now if we go all the way back to our definition at the top, let's just summarize. We've now kind of described first a ledger that we use to record the entire history of a database so that we could reconstruct it at any point and know what the current state is. So your ledger might contain cryptocurrency, or it might contain a virtual computer, but it's in a database for everyone to use. Then what we wanted to do was we wanted to make it tamper resistant. So to do that, we turned our ledger into a chain of blocks where each block contained the hash of the previous block, so that if you went back and changed, say, block 1, it would no longer validate from block 3. Following the links wouldn't work. Then now that we had this tamper resistant ledger, we wanted to distribute it around the world so that everybody could agree on the rules. And that's when we needed the consensus mechanism. So the point of the consensus mechanisms was to prevent someone or anyone taking control of 51% of the network and starting to break the rules. Double spending money, making programs run incorrectly on a virtual machine, and so on. And so what we've ended up with is a blockchain as a distributed tamper-resistant ledger. Are there any questions on that part?
No, it's clear.
Cool, great, I'm glad. So there's one more part to the definition, which I'll talk about briefly, but I've just put this as optional because if you're not interested, you can ignore it. But this is the space efficient part. So you can imagine that as we add blocks, all containing the data from the past, it uses a lot more space than just maintaining the current database. If I'm using 3 people and I want to store our current bank balance, that's 3 lines in this case, or it might be 3 bytes in a database. If instead I'm storing the complete history of all the transfers between us, and this has been going for 8 years, then this data is a lot more heavy space-wise, uses a lot more space than just the database. So it's kind of a trade-off in that we've got the full history, but to store it is really tricky. What would be nice is if we could store the whole history in a verifiable way, but allow people to get rid of transactions they don't care about, so that I wouldn't have to care about transactions made between Neela and Aleph, right? I don't care about your transactions, I only care about ones involving me. I want to be able to securely discard the ones that don't belong to me. And the way that kind of works is that we use a new cryptographic construct based on hashes called a Merkle tree. And you can really quite easily see in this diagram that a Merkle tree is just, it's like a binary tree in computer science. You've got hashes that are then hashed, and so on. And I'll give us an example of that. If, say, I have 4 transactions, let's go TX1, TX2, TX3, TX4. I might just do this like this. Then for each of these transactions, I'm going to hash it. So I will copy TX1. Do the same for TX2, TX3, and TX4. So these have all got a hash. Now I'm going to split them into groups of 2, and I'm going to hash together the hashes. So this might just look like this. We might copy the hash of TX1, then stick on to the end the hash of TX2. So those 2 hashes are together, and we end up with this new hash like this. And stop me if this doesn't make sense, but I'll do the same for TX3 and 4. So we're sticking those hashes together, and we get a new hash that looks like that. So now we've kind of compressed our 4 transaction hashes down into 2 hashes. And then finally, we'll do that again. So we'll take this 16 dB, which is the hash for TX1 and 2. We'll do that for 3 and 4 as well. And we'll end up with this final hash. So then this single hash here, which encompasses the hashes for TX1, 2, 3, and 4, is called the Merkle Root. And in Bitcoin, instead of storing all of the transactions in the block within the actual block itself that goes to everyone, all that we store is the Merkle Root. Then what that means is that that's what's called the root hash here, so the Merkle Root hash. And we have that tree just like I did there, so TX 0, 1, 2, 3. I've done 1, 2, 3, 4, but the principle's the same. So if I then want to verify that these 4 transactions are in the block, then I can just redo that hashing and check that the Merkle Root matches the one in the block, which is good. I've already saved some space by not having to store, the full list of the transactions if I'm not interested at all what's going on in that block. But say that I still want to store all the transactions that are related to me. If I was interested in, this block 0, and TX3 was created by me, to be able to get the root hash, the kind of naive way of thinking about that is that I also have to store all the other transactions in the block so that I can do that hashing and reconstruct the root. But we can do something called pruning here, and we can realize that I don't actually need to store TX0, TX1, or hash 0, hash 1, and so on. All I need is the kind of links that are relevant to my transaction 3. And from just those 3 hashes and my transaction, so the 2 hashes, sorry, and my transaction, I can validate that TX3 is part of this block. So I can validate that my money was sent correctly in this block without having to store all of this information here. So it's much more space efficient. We've kind of compressed the information we need to store for the transactions that we care about. So yeah, in summary, we kind of prune the transactions that we're not interested in to save space. And that gives us a space-efficient, distributed, tamper-resistant ledger. And that's our final definition. The only other thing to note is that doing this reconstruction here, in case you need to talk about it later, is called a Merkle proof. You're proving that transaction 3 is part of the Merkle tree. So it's a Merkle proof, where you're kind of reconstructing the hashes along the way. Okay. Sorry, that is a big dump of information. Are there any questions so far? Cool. So what I want to do now is, firstly, we'll go through that Bitcoin white paper and I'll kind of highlight each of the things that we've talked about so that you can go in your own time, read through it and make sure you kind of know what's what. Then what we'll do is kind of together, we'll go through the Bitcoin blockchain, like the actual data in the Bitcoin blockchain, and see all of this information in practice. So firstly, let's jump back to this Bitcoin, a peer-to-peer electronic cash system. You can see, firstly, there's a bit of an introduction. It's a peer-to-peer version of electronic cash, and it kind of spells out the advantages of blockchain. So you no longer need a trusted party. You don't need a centralized network to control your money. People can share their data freely. They can't be cut off from payments. A dictator can't come into power and lock off a subset of the country, and so on. And in fact, Bitcoin kind of came out of an ideological opinion that relying on financial institutions and relying on governments is not great for mankind. And whether you agree with that or not, it has resulted in Bitcoin. So that's quite cool. We can see in the first ever block of Bitcoin, so the block 0 Genesis block, Satoshi Nakamoto, whoever they are, actually put a secret message in the block. And it is a headline from a newspaper that just says, like, it was printed in the Times and it says, Chancellor on brink of second bailout for banks. So the kind of context of Bitcoin is that it was created just after or just during the 2008 financial crisis. So the governments were bailing out banks, people were losing their homes, but the kind of banks survived it all because the governments were bailing them out. And Satoshi Nakamoto and kind of the early Bitcoin and blockchain pioneers thought that this was wrong and that they would create their own digital currency. And so that it's kind of written in the introduction. Then what it talks about next is the transactions. This is section 2 here. And this is what we're talking about here. Each of these is a transaction. I'm sending money in a transaction from me to Alif for 10,000. And it goes into detail about how that's done that we've kind of glossed over there. Then next, it talks about grouping those transactions together into blocks and putting them into a tamper-resistant ledger. So it's done in a lot less detail than we went into, but the diagram's the same. Then it talks about how proof of work makes that network distributed and peer-to-peer and still secures it using a consensus algorithm. So it's got that description of the consensus algorithm there. Talks about the incentives for running a network. It says that you've got Bitcoin rewards for your computing power and so on. It talks about the Merkle tree that saves space in the ledger and makes it space efficient. And then finally, it talks about some kind of Bitcoin specific stuff, like how the actual coin transfers work. It's a bit more complicated than just transactions like this, but it's not really relevant, so you can skip over that part if you want. It then talks about kind of the difference between the traditional privacy model, so how a bank would work, and the new privacy model of Bitcoin. In the traditional privacy model, we have this trusted third party, which could be the bank, the government, the Federal Reserve, and so on. And us as the identities submit transactions through that trusted third party to whoever we're sending our money to, the counterparty. And we've got this kind of walled garden around that blocks off the public. Now, in this new privacy model, we have our identities, and in Bitcoin, that's just an address. There's no way to tie it back to your physical identity. I might have 10,000 Bitcoin addresses that you can't link back to me. And we send out these transactions, which get included in blocks, and that goes out to the public. So everyone can see it. Everybody knows that the rules are being followed. and everyone can validate that ledger. What we'll talk about, starting from next week, is what we want to do if we want to start hiding the contents of these transactions. Obviously, if I go into Bitcoin and I know someone's address, I can see everything that they've done. I can see who they've transferred with and so on. So if I'm a government and I want to see, has Cable purchased any drugs using Bitcoin, for example? Has he committed any crimes using Bitcoin? I can go back and look at those transactions because they're all public. So a lot of blockchains view this as a disadvantage and have worked out, secure privacy mechanisms, which we'll talk about in the future, that mean that even though the whole ledger is public, the contents of the transactions can be hidden. So it's a bit more, secure and private for people rather than just putting all your information out on the internet. And then finally, it ends with just looking at the probabilities of someone successfully attacking the network, which you can read the maths of. So yeah, I've said a few times, I would really recommend reading this document. I'll send a link to everyone in Telegram. It's really, really good overview of that. Okay, now let's put it all together. Let's go to the Bitcoin blockchain and have a look around. So I'll just make this full screen. But this is, a publicly available blockchain explorer. So you guys can explore alongside me if you like, blockchain.com/explorer. And we'll kind of go through each of these sections and see how they relate to what we've been talking about. The first thing to note is the price of Bitcoin. So one Bitcoin is now, what, $40,000 US. So you can say that's extremely lucrative. And if you bought it back in 2008, you'd be a billionaire even at this point. But, being developers, being interested in blockchain as a whole, we're going to ignore the price for now. And we're going to look at the technology. So in this latest blocks list, we can see each of the blocks that have been created. So let's first look at the last block, which is number 685,000. We created 3 blocks in our example. Bitcoin's up to over 600,000. And I'll click through and we can actually look at the details of what's in that block. So remember, this is like the list of our transactions. We can see that the block hash here starts with a certain number of zeros, which is less than the difficulty. That's awesome. So we can see that's maybe like 20 zeros there. So whoever mined this, whoever created it, was able to find a nonce that gave us a hash with that number of zeros at the start. And we can actually see what that nonce was. So we can see it's 2 billion there. Is that billion? Trillion? 2 billion. So they might have had to try, depending on where they started, 2 billion different hashes before they could find this block. So that's why it needs so much computational power. We can see also the Merkle Root. So that's that tree that we reconstructed from the transactions. It results in that single Merkle Root hash. We can see what that is for this block. We can see that the blocks in Bitcoin are much bigger than the ones we were looking at in our example. Instead of having 2 or 3 transactions, this one had nearly 3,000, which is all compressed into this single hash, right? So you can see that the 3,000 different transactions between people compressed into a single hash is very space efficient. And you can see like the total size on disk of this block. You can see that in total, 28,000 Bitcoin was transferred within this block, so within the transactions in this block. And the reward for the miner, for the person who created this block, was 6.25 Bitcoin, which, considering the price of Bitcoin is $40,000, is a fair amount of money. So it's pretty lucrative to be a miner. We can also see that in the confirmations here, this block has been confirmed once. In Bitcoin, again, we want to generally wait for about 6 confirmations to know that a transaction or a block has been included. So if I had sent money within this block, I would want to wait a bit more time before I would send out the goods that I was being paid for and so on. What's interesting to look at here is also the miner. So the miner is the name for, any miner on the Bitcoin network is someone who's trying to create blocks. And the miner of this specific block is someone called Antpool. In Bitcoin, because it's so hard to find a block, you might only say find one in your entire lifetime of 80 years, which isn't economically feasible. Sure, you might make $200,000, but that $200,000 might come in 40 years. Most people who try and create blocks on Bitcoin do it through what's called a pool. And here we can see this pool is called Ant Pool. And a pool is just a bunch of people all agreeing that we'll all mine together, and whoever wins the reward will split that amongst us. So on average, you'll receive the same amount of money, but it's split over time rather than coming every 20 years. Yes, it's a much more economically viable way to find blocks. And you can also see on this block explorer, you can see Ant Pool here has in total made 43,000 Bitcoin. Its final balance is 216 Bitcoin. So almost all of the Bitcoin that it's earned through mining has been transferred to the people in the pool, to the users in the pool. I think Ant Pool, just out of interest, is in China. And you'll find a lot of the big pools and a lot of the big miners are in China because the electricity is really cheap. And they're usually next to hydropower dams. And they get super cheap electricity so that it's more economically viable to mine Bitcoin. Okay, so let's go back to our block. We're still looking at the same block, but we'll scroll down now to the transactions in the block. And this is a list of all of those transactions, so that those 2,800 transactions that have been included in this block. Just the regular transactions here are exactly the same as the ones we're looking at in our example blockchain. So whoever has this address has transferred 0.17 Bitcoin to whoever has this address. They've actually split some, but that's okay. They've transferred in total 0.169 Bitcoin. They've paid a slight fee to the network, which is used then to incentivize miners. And that's been confirmed once, right? So this is the vast majority of transactions in Bitcoin are just people sending money to each other. We can also see the first transaction is special, and that's called the Coinbase transaction. And this is that mining incentive, the reward. So they've been rewarded with 7.32 Bitcoin for creating this block, for finding it. And that's why it says Coinbase there. Now, there are a few other different types of transactions in Bitcoin, but they're not really as widely used. There's kind of very basic smart contract functionality, but we'll talk a lot more about that when we talk about Ethereum. Okay. Any questions on the kind of block and transactions?
I think I need to review them a bit more.
Oh, yeah, great. I'll send the slides through as well. And if there's any more questions too, we can put them in Telegram, or I think Telegram is probably best because then everyone can see them.
Yeah.
And if we look then at our kind of overviews.
After this session, I will add everybody on Telegram. So if you have any questions and anything you need to know from the panel, so you can.
Yeah. Yeah, absolutely. Just some kind of interesting stats here. We can see that, we've now reached, there's 40 million addresses or 40 million users, although one person might have more than one address, that have at least some Bitcoin in it. So we said the network is growing over time. This is from January to May. The transaction volume is increasing. That's the large transactions, but we look at the transactions. Don't know where the full chart is. You can also see kind of the concentration of whales, and a whale in cryptocurrency is someone who owns heaps and heaps of cryptocurrency. So in this case, they've defined a whale as someone who owns between 0.1% and 1% of Bitcoin. And there's one person who owns over 1% of Bitcoin. So imagine how much that's worth, 269,000 Bitcoin times 40,000. Yeah, that's pretty cool. Only one more thing to look at, and that is what's called the Mempool. Now, remember we're talking about the consensus mechanism before. And the way the algorithm kind of works is that first everybody sends their transactions to every node, and then the nodes create blocks that contain those transactions. So if I want to send my $10,000, I'm going to send that to all the miners. And I'm going to say, can you please put my transaction into your block? And that's just in this, I go to my consensus mechanism. That's this 1 and 2 step, right? I'm sending out new transactions. And the transactions that haven't yet been put into a block are called the mempool. So you can think of these as, say a block can fit 2,000 transactions and there are 10,000 transactions waiting on the Bitcoin network. You'll have 8,000 that are still in the mempool. And if we look back at the Blockchain Explorer, you can see the size of that mempool, so the size of the unconfirmed transactions over time. We go back to say 30 days. You can see that in kind of the middle of May, then the backlog started being cleared a lot, but now it's come back up a bit. So these are all transactions waiting to be sent. To make sure that miners choose your transaction, say, we've all sent a transaction, I want mine to go first because it's a really important transfer. I can choose how much money to include as the fee. And if my transaction is chosen and put into a block, whatever amount that I put in as the fee goes to the miner. So the more important my transaction is, the higher fee I will pay, and the more chance it is of leaving the mempool and being included in the block. Okay, so yeah, jump onto this in your own time as well. Have a look through at some of the blocks. You can see that they're coming quite slowly now, but it's cool to see what the transactions are in them. If you've ever sent Bitcoin, type in your transaction or your Bitcoin address and have a look at what else was in that block with it. And you can kind of start to understand what's going on behind the scenes. Remembering that really all that Bitcoin is and all that blockchains are is this distributed tamper resistant ledger. So it's a database that's shared amongst people in a trustless way, which means that there's no central point of failure. There's no authority for the whole network who controls the rules. It's a kind of democratic process that's secured by a consensus mechanism. And so I will finish there for today. I know that's heaps to digest at once. I think you've probably all received a pre-reading email. I'm not sure. Did that go out? There was an email with a few, like a video link and a couple of documents.
Karel, I have a question.
Yep.
In the first material, we have looking for the token creation. So, and in this course outline, I didn't get anything token creation. So, could you please add that things, because we have some work for creating token for the client. So
sorry, you're cutting out a bit. Sorry, you're booming a bit. I can't understand.
In the previous code outline, we have including token creations, blockchain token creations. So today we have received one, but in that curriculum, I didn't see the token creation. So could you please add that things for us? Because we already had some work for the token creation.
Yep.
Thank you.
Cool. So next week we'll be looking at we've seen kind of the technology. We've learned what a blockchain is. Next week we'll start to look at how it looks in practice. What are the major blockchains? Bitcoin, Ethereum, Monero, Litecoin, Dogecoin. There's a gazillion blockchains out there. What their advantages and disadvantages are. How you actually start to use a blockchain. The different, and then particularly focusing on the different use cases beyond cryptocurrencies. So, cryptocurrency is an easy example when we're just learning about it, but it's also not the only use case. And I think there's a lot more exciting use cases, which we'll talk about next week. Cool. All right. Thanks, everyone.
Thank you, Kato. Thank you so much.
Let me stop this recording.
Thank you, Lina.